let's look at the odd symmetry, and we see the ft has odd symmetry if ft is equal negative ft, f negative t. So this is basically the ft is an odd function. If you think about odd function, as essentially you can use the origin as the pivotal point, and you can just rotate the other half of this waveform by 180 degrees, so they will match the other half. And that's kind of the intuitive way of looking at this. Or you can match point by point and see if whether ft is equal negative ft. And in any case, let's see in this one, what would be what would this impact it would have on the Fourier coefficients. And let's first look at, we still have ft that's equal to the sum a0 plus the sum over an times the cosine n omega t plus bn times sine n omega t. And f negative t, we just did that, right? I should copy that. And f negative t, that's equal a0 plus the sum of an times the cosine n omega t, because n omega negative t, take cosine that's the same as cosine n omega t, and minus bn times sine n omega t. And for ft equal negative ft, f negative t, and then we will have a0 equal negative a0, right? If we compare the Fourier coefficients, and an equal negative an. So therefore we have a0 equal 0 and also an equal 0 for n equal to 1, 2, to the all the, and the bn we don't really have any limit on or constraint on the bn, right? So this is the it's also kind of intuitive to make sense, because the function itself has is an odd function, right? The cosine terms, actually cosine function are even functions, so you can't really have even terms in the odd function, right? So that's it. Let's look at an example of what this waveform will look like. Here I have this sawtooth waveform. This sawtooth waveform passes through the origin point, and if you look at this, definitely this is going to be ft has the odd symmetry, right? Has odd symmetry because the point here, let's see, equal 0.5, this is negative 0.5. Let's see if you choose a point 0.25, 0.25, and let's see negative 0.25, and this is going to be equal negative 1, and this is positive 1, so on and so forth. You can rotate the other half, as I said, using the origin as the pivotal point, and then you can that should fold right on top of the other half of the waveform. And it has odd symmetry, like row 2. Since ft is equal negative f negative t, right? So therefore we have the bn's. We only need to find the bn's, right? The an's, let's write this way. An is going to be 0 for n equals 0, include the DC component and also all the AC ones. 2 . These are all the an, so we don't really need to find an. So let's see the waveform. This has the t is equal 0.1, and therefore omega is 2 pi over t, that's equal 20 pi. And the function, we're going to integrate this, and over, let's choose the waveform, the integration period from negative 0.05 to 0.05. And during this integration interval, we're going to have the ft is just a straight line, right? What's the slope? The slope is going to be 2 over 0.05, right? So that's the 40t during this interval. So and therefore we can do the integration now, I think. So let's start with the Bn. So n start from 1 to infinity. And Bn is going to be equal to 2 over t. And go the integration from negative 0.05 to 0.05. Right? So ft and sine n omega t dt. And let's plug in the numbers. And the 0.2 t is equal 0.1, so I get a 20 there because 2 divided by 0.1, that's 20. And I have negative 0.25, negative 0.05, and to positive 0.05. And ft is equal 40t, and the sine n omega t, n is 20, omega is 20 pi, so n times 20 pi t dt, right? And we need to integrate this in a couple of steps. So first step is we will change this function and to so we move the 40 outside, so 20 times the 40, and then we divide this n times 20 pi. And now we can move this inside this d here, and we have negative 0.05 to 0.05, and I have a t times d sine, not sine, it should be cosine n times 20 pi t, right? And I should have a negative sign here because the cosine x is equal to negative sine x. And based on that, so let's see, this 20 may be canceled, so we're not going to carry this. And based on the chain rule, we have x dy is equal dxy minus y dx, right? And if we think they treat this as x and treat this as y, and we're going to have a negative 40 over n pi, because that 20 is canceled there, and we're going to have a t times the sine, because dxy, we just evaluate that at the upper and lower limit, sine, not sine, cosine, because y is cosine. Let's see, just use 20 n pi t, and we evaluate the t at equal negative 0.05, and the upper limit is 0.05. And then we'll have the minus the xy, because I have another negative sign, so I'm going to plus here, plus y dx. Y is, so I need to carry all the things in front of the integration, and I have a negative 0.05, and cosine 20 n pi t, and dt. And this integration I don't really need to work on, because this is equal to 0, I know for sure, because this is a sinusoidal function, and this will integrate over a fundamental period or multiple fundamental periods. So we don't really need to worry about this, because the t, if you look at this cosine function, the t is just for this one here. The period for this one is 2 pi over omega, which is 20 n pi, yeah. So we got 1 over 10 times n, or we got a 0.1 over n. So the period is n, the fundamental period, which is 0.1. So therefore, if you integrate the fundamental period, that means that's n times the sinusoidal waveform. So therefore, you get a 0 for sure, and we're gonna only need to care about the first term. The first term here we have, so I'm gonna have 0.5. Let's just substitute things in. And by the way, the when t equal negative and positive, cosine function is the same, right? So we can just get this. We can get a negative 40 n pi times cosine 0.5. What's 0.05 times 20? That's 1, right? So that's 1, that's n pi. And times let's just write it in 2 steps. So I don't want to get too many steps. 0.05. So t is equal to 0.05, right? So minus the other half, and we do plus 40 n pi, and we have cosine. Cosine negative n pi. That's equal n pi, right? So we have times t. T is negative 0.05. I think we get many negative signs, right? I think we're getting correct. Or we have, yeah, I think we are getting correct. So if you're getting confused, let's see, we do these. So we have negative. So in that case, we will have a negative sign here. So we work this couple of steps, and I think this is not confusing, right? So we have cosine n pi factor out, and we have this one here, and we have oh, I don't have n pi. I have cosine. Yeah, so I have 40 n pi outside. So I only have this term. So this term will double this, right? So that's 80 over n pi times cosine n pi times 0.05. So 80 times 0.05, that's the that's 4, right? And also cosine n pi is equal the negative 1 to the power n. Right? Every time you add a pi, because the cosine pi is negative 1, right? Every time you add 1 pi to the cosine function, you get negative 1. So you have multiply to the power n, and therefore we have the Bn is finally Bn is equal negative 1 to the power of n plus 1, right? And times 0.05 times 80, that's 4 over n pi. So this is the final solution, and let's look at whether this makes sense using the Google Colab. And here we have let's see, this is the even one, let's see the odd one, and we have so we use the result here, and with this original function again here I'm defining the original function, the sawtooth that's passing through the origin, and this is the blue curve we have here, the blue curve passing through the origin, right? And has magnitude from -2 to +2, and over a fundamental period of 0.1, right, goes from -0.05 to 0.05. So that's the original waveform we have, and I'm utilizing the Bn coefficients. So of course the Bn we start from 1. So if somehow you give a 0, I'm just defining this as 0. And I'm having -1 to the power n plus 1 times 4 over n pi. That's the Bn function we're going to use. And this is a reconstructed waveform that has that's sum from the 1 from so that's a Bn times sine n omega t. Now I define the omega, the w here is 2 pi over t, and this is the waveform we approximated using the harmonics. Let's see if we use 100 as we did before, we should see closer matching there. And oops, I did 1,000. Let's do 100, and I'm gonna run the code. So this is the 100. This actually do a closer matching. So these Fourier coefficients definitely are correct, right? So next I'm gonna take a look at the half waveform symmetry. I'm gonna see you in a moment.